All right, good morning, everybody. So we're now at the point in the course where we're ready to start talking about how you can actually build reusable components. And so what we're going to do today is we're going to start to look at how to create an actual data structure that you can either use in your own programs or you can distribute to other people for use in their programs. And so what we need to talk about right now is how you actually organize a C program that's not just one main function or not just made up of a few functions. All right, so when you are going to make a data type, typically what happens is if you're making the data type for somebody else to use, you typically don't give them all of the source code for the data type. Right. Typically what you do is you take your source code, you pre-compile it, and you distribute your code as a pre-compiled library. Now the people who are using your code, they still need some way to access the library, and so they need to know what features are provided by your source code. So those features go into something called a header file in C. Right, so when you make a new type like point2, or in this later on today, we're going to implement a list, you typically, you're creating functions that accompany the data type itself. Right now, in an object-oriented programming language, you bundle the information that the data structure contains, plus the methods or functions that operate on the data structure into one place. Right, you bundle it into a class. That's the whole point of object-oriented programming. In C, it doesn't have the class mechanism. And so what you do is you separate the declaration of the features and the implementation of the features. Declaration of the features go into the header file, right? And typically that header file has a .h extension. Right? Any C source code file that wants to use your data type would just include the header file and then link to the library that you provide. So your definition of the functions, they go into a separate C source code file. Right? So for the point2 struct that we looked at previously, we'd like to turn it into an actual data type so that people can, you can use it. So I'm just going to do a few functions here. Right? So if you have so for our point2 type, we'll have these four functions here. Right? So we'll have a move function. So move takes a point pointed at by P and moves it by delta x and delta y. Right? Changes the x and y components by dx and dy. Right? And that effectively moves the point. Point2 underscore multiply underscore mult takes a point P that's pointed at, takes a point that's pointed at by P, multiplies the coordinates of the point by S, equals tests if 2 points are equal. Now this is the first time that we've seen const, I think. So in const, you can mark a variable as being const when you declare it. So in this case, we don't have a pointer to a point2, we actually have a point2 struct. Right? So saying that this point2 P is const says that you cannot change the state of P. Right? If you try to change the x or y coordinate of P inside this function, the compiler will emit an error. Right? It says you're trying to change the state of a const object. Right? And the same is true here. Right? So if you ever see const in a function somewhere, the function is trying to tell you that it doesn't change or modify the state of the thing that you're passing in. Right? Similarly here, we're going to take a point P. We're going to return a quote-unquote string representation of the point P so that someone can print out P without having to do it manually themselves. Right? You're going to see here that when you generate the string representation of a point, or of anything in C, it's actually quite awkward to do. All right, so we're going to separate the implementation and the declaration of the data type and the functions by putting the declarations into a header file. We're going to put the definitions into a source code file. So this is showing you the start of the header file for point2. All right, so I'm going to make a header file called point2.h. Right? Your header file always starts with these two lines here, and it always ends with that line there. Right? So there's an if and def, and there's a define, and then there's an end if. Right? So if and if point2 underscore h. Typically, this is in all caps. Right? So it's the name of your header, it's the name of your type underscore and then capital H. Right? So if and def is a preprocessor directive. So it's not read by the compiler, it's read by the preprocessor. Right? So the preprocessor, this command here says if not defined. Right? So it's looking for a name, point to H. Right? And so if the preprocessor has not seen this header file before, then point to H will be undefined. Right? And the stuff inside the if statement will run. Right? So first time you include this header file into, the first time you include this header file and compile a source code file that includes the header file, right? Everything between the if and def and the end if will be included into your source code. Right? Okay, now the second time, the third time, and the fourth time that someone includes your header file, you don't want to re-include all of the declarations again. So the very first thing we're going to do is we're going to define point to H. So this just declares a name point to H that the compiler is now, that the preprocessor is now aware of. Right? So if the preprocessor has not seen point to H, define point to H. The next time someone imports or includes this header file, the contents of the header file will not be inserted into the program. Right? So this this is called the header guard. So this ensures that the header file is only ever included once into your compiled program. The reason you need to do this is because if you're defining, your header file is allowed to include variables. So if you define a variable multiple times and you try to include it into multiple compilation units and then try to link them together, that doesn't work in C. Right? You end up with a bunch of static variables that all have the same name, and you're not allowed to do that in C. Right? That's also the reason why these names of the functions, they all have .2 underscore in front of them. Right? So in C, you can't have two functions with the same name in the same program. Right? And so when you're creating a data type, what often happens is you give your data type a name, you hope no one else has used that name, in this case, we're hoping that no one else is going to create a type called point2, right? And then for all of the functions that are associated with your type, you append it with either the name of your type or some abbreviated form of the name of your type, right? So when you read C source code, it's very common to see stuff like point2 underscore move, right? It's also really awkward, but that's because C doesn't let you declare two names with the C does not let you declare a name more than once inside of a program. Oh, I guess I skipped this slide. So every header file should have an include guard. That's this if and def define and if structure here. Whoops, sorry. Come on. Right? So that prevents the header file from being included more than once in a compilation unit, and it's the preprocessor that typically reads in this that processes the include guard. Okay, so once you've got your include guard in, now you just insert the declaration of your functions in between the define and the end if. Right? So I need one of my functions is going to return a Boolean, so I need to include standard bool. Right? There's my structure, so there's my point2 structure definition in this case. Right? There's my type def of the structure, so I can just use point2 instead of writing struct point2 everywhere. Right? There's the declaration of my functions. Right? And that's the contents of the header file. Right? So the header file just advertises or declares what features will be provided by our type point2. Right? Okay, any questions about the header file? Right? So remember when you make a header file, include guard, right? So if and def define and an end if, right? That prevents this contents of the header file from being included into the same compilation unit more than once. All right. So there are my functions. We need the definition of the function somewhere, so they go into point2.c. Right? So a separate C source code file contains the definition of the functions. If you have a reason to, you can put it into multiple source code files. Right? But our types are relatively small, so we're just going to put everything into the same source code file. So into my point2.c source code file, right, I'm going to include the headers that I need. So I'm going to need standard IO to generate a string representation. I need standard lib.h for some of the other functions that we need it for malloc in this case. And then the very next thing you do is you include your header file right? So by including the header file we just created, that drops the contents of the header file into this source code file, right? So it declares the structure and it declares all of the functions that we're going to implement. Right? So when you create your own your own header file and you include it into a program, it's always the double quotes around the header file name. Right? The angled brackets, they indicate either the standard library header files or the system header files that you're programming for. Right? So if you're using some of the Unix header files, they'll also be inside of the angled braces. Right? Otherwise, it's double quotes. Right? Okay, and now you just drop in the implementation of your functions, right? Which is pretty straightforward in this case. Right? So to move a point by dx and dy, assuming I have a pointer to the point, right? I can just write p arrow x plus equals dx, right? So add dx to px and update px, right? It's a pointer in this case, so I use the arrow to dereference the pointer and access the member at the same time, right? Do the same thing with y, and away you go. Right? Multiplying a point, it's exactly the same as moving a point. You just multiply x and y by s. Right? Equals, well, I want to compare the x and y coordinates of p with the x and y coordinates of q. Right? So px equals qx and qy equals qy. Right? This doesn't work if your point coordinates can be not a number, because not a number never compares to itself. It doesn't compare to anything as being equal, not even itself. Right? So if you have to deal with not a number, that's not going to work. And then finally, this awful function here. Right? So in in Python or Java, generating the string representation of something is very easy. In C, it's very awkward. Right? Because in C, you have to deal with the fact that there is no string type. And so you have to allocate space for an array of char, right? You have to remember to include the null terminator at the end of your string, right? You have to figure out how much space do I need for the array, and so on and so on and so on and so on, right? So it's no fun generating the string representation of stuff in general, right? Most libraries that you'll end up using don't actually generate the string representation of something for you. You have to do it you have to do it yourself. So I'm going to show you this one function that does generate a string representation of a point, and then I'll explain what the disadvantages are of doing this. Okay, so step one, I need to figure out, so first of all, I'll tell you what the string representation is. So it's going to look like a round bracket and a closing round bracket at the end. There'll be a comma and a space, and then this will be the x coordinate here, so something like 1.5, 1, 2, like that. And let's say 2.5, 1, 2, 1, 2, 3, like that. So it's going to look something like that. It's going to be the x coordinate of the point, the y coordinate of the point, there'll be a comma and a space. Right? So you need to figure out how big is this thing going to be. Right? So I need one for the opening bracket, I need another one for the closing bracket, I need two for the comma and the space, so I need 4 characters at least. Right? So there's the 4. Right? Now I need to figure out how long can that number be, right? And how long can that number be? The answer is there's no actual good answer for this, right? So I happen to know that p is being printed out as a double in this implementation, right? You've got roughly 15. That number might be too small, right? So this may not work for every point that you can conjure up, right? You've got roughly 15 characters in a double at most, right? Roughly. So I'm just going to use 15 here. This number is probably too small, right? I also need the null terminator, right? So there actually should be probably plus another 1 here, because I need the \0 at the end of this string. Right? And so counting the number of characters you need in something is not easy. It's not at all obvious how you should do this, right? So there's a big question mark here as to whether or not that's big enough for every possible point. But let's assume that it is, right? Now I need to allocate an array to hold the string in, right? I can't use a plain old array here, right? So I can't write char, buff, square bracket, something, right? I need a dynamically allocated array because I'm going to return a pointer to the first character of the array back to the caller. And that array can't disappear after this function disappears. Otherwise, the caller can't print the string. Right? So we have to dynamically allocate the buffer. Right? I guess if we're going to follow the standard device, we should check if the return pointer is not null. Right? If it is, we're going to return null for the string. Oh, notice this, this returns a pointer to a car, right? So it's going to return a pointer to the first character of this array. And now I have to take the x and y coordinates and put them into a string. So the function you want to use there is sprintf. Right? So printf is the function that prints something to standard output. Sprintf prints something to a string. Right? Use it in the exact same way that you use printf, except for your first argument to the function is now the string that you want to print into. Right? So sprintf buff will print something into this array called buff. Right? Buff is short for buffer, which is sort of a generic term for a chunk of memory that you can use to put stuff into. Right? Okay, so now I'm going to print this that into the buffer. Right? So round bracket, comma, space in between. I'm using %g here, which we haven't seen yet. So %g is the floating point conversion that picks between either scientific notation or the standard notation, the standard format like that. It tries to pick the best one. It tries to pick the one that produces the quote-unquote nicest output, right? Just look at the printf documentation to see how it determines which form it uses, right? I'm just using it here to show you that it exists, right? So px gets converted by the first %g, py gets converted by the second %g. Right? Sprintf returns the number of characters that are printed into the buffer. Right? It also appends the \0 for you at the end. Right? So this is going to deal with the \0 for us. Right? So n is the number of characters that gets printed into the string. Right? Notice there's no way to tell sprintf to restrict the number of characters to the length of the buffer. Right? There's no way to do that here. So if that buffer is not big enough, sprintf may overrun the end of the buffer. Right? So you have to watch out for that. This thing returns number of characters. It is number of characters, yes, right? So if it's less than 0, there's an error, so it couldn't print the first thing. So in other words, it couldn't convert the p.x, which shouldn't happen, right? If the number of characters is bigger than or equal to the buffer size, there's a problem, right? It's overrun the end of the buffer. If we're lucky, nothing crashed, right? So here I'm going to try to I'm going to deallocate the memory and then return null to indicate that we couldn't print the string successfully, right? And then finally, you can return a pointer to the first character in that buffer, right? So generating the string representation of something is not trivial in C, right? There's all sorts of things that you have to worry about. The other disadvantage is here, if someone's using this function, they're stuck with whatever you chose here, right? So there's no way for them to print the string in a different way, right? They might want a different number, a different precision, or a different width when they print out the string. Here, they're stuck with whatever you give them, right? And so for that reason, well, for two reasons, right? One, it's hard to generate the string representation. Two, because you don't know what the user is going to want for their string representation. It's often the case that these C data structures, they don't have a string conversion function in them, or a print to a string function in them, right? It's awkward to do, and you can't always generate the output that the user wants. Having said that, you should really wonder how Python and Java manage to print out floating point values, right? It's no small task to print out the decimal representation of a floating point value. Okay, so I'm just going to leave that for now, right? If you don't really understand what's going on here, don't be too concerned. We're going to come back to another example later on, right? All right. So moving into the next, so there's a, oh, sorry, let's see slideshow. So that's the complete, that's our quote unquote complete point 2 type, right? So that's all I want to do for point 2 because it's a very simple data type, right? If you wanted to, you could add more functions to it and play around with it and see what you can do with it, right? So instead, I want to go on and implement a more complicated data structure. If you're reading the notebooks, then the relevant notebook here is a simple string type. So this implements a string for you in the notebooks. I'm going to do a list instead, but a list is essentially, so a string is essentially a list, right? A string, well, a string resembling something that Python or Java gives you is more or less a list, right? It's just a list of characters. So this notebook, even though it doesn't look like it corresponds to what I'm about to talk about, it's more or less the exact same thing. I'm going to do a list of int instead. Somewhere here. Right, so we're going to do an array-based list. Right, the source code is on OnQ. Right, there's a zip file that you can download from the lectures page. All right, so I'm just going to quickly review what a list is, very quickly, and then we'll get into the implementation. Right, so we know what a list is, right? It's just a sequence of elements. The elements have an index. Right, the size or the length of the list is the number of elements in the list. Right, and there's the notion of the empty list, right? The list with nothing in it. The capacity of a list, that's the maximum number of elements that you can put in the list, right? So a Java list or a Python list, it has no fixed capacity, right? The capacity of the list changes as you add elements to it, right? So in other words, it's arbitrarily resizable. So that's what we're going to try to do as well. Right? Adding an element to the list adds the element to the end of the list, right? Which increases the size by 1, right? And it's convenient, it's often convenient if the capacity changes automatically as the list becomes full, right? So you fill up the capacity of the list, and then we would like you to be able to still add new elements to the list, so we're going to have to manage memory ourselves in this case. Right? There's your empty list of size 8, capacity 8, right? Size 0. So there's an array that we're going to use to hold the elements of the list, right? Just like in Java, right? There's nothing in the, well, sorry, conceptually there's nothing in the array, right? In actuality, there's always something in an array, right? But we don't know what the values are, and we don't care, right? For the empty list, there are no valid indexes. So if someone tries to get or set an element of this list, it should fail. Right? There's a list with one element in it, so there has one valid index, right? So we can get or set that element, right? There's 2, there's 3, and so on, right? So when the array has 8 elements in it, sorry, when the list has 8 elements in it, we can get or set any of the elements in that array. All right, so getting or setting an element, so I can get or set that the fourth element in the array, right? That's just the element at index 3, right? We know this from 124. Right? So if you get that value, it returns the value sitting in the array at that location. If you set that value, it overwrites the value sitting in that location. Right? If you try to get or set an element of the, if you try to get or set a non-existent element, that should fail. Right? So we need some way to indicate failure in C. Right? Adding to a full list. So if the array that's holding the elements of the list is full, right, and you try to add another element to the list, that should succeed, right? And so we need to make this array bigger, right? And so now we're going to use realloc, right? So we're going to allocate the original array using malloc, right? When the thing becomes full and we try to do something that requires adding more elements to the list, we're going to reallocate this array, right? Remember, reallocating the array makes the array bigger, and it copies over all of the elements for us, right? So we don't have to worry about the copying. The strategy that we're going to use when you add an element to a full array is we're going to double the existing capacity, right? So when we add to this, do I have a picture here? Yes. So when we add to this array, right, we're going to realize, oh, we have to make the array bigger, so we're going to make it bigger by a factor of 2, right? We're going to double the capacity. So when you add to that previous list, what ends up happening is you end up with a new array, right? And now you can add into the first location of, sorry, you can add into the newly allocated array now because there's space. Right? We're going to implement insertion as well. So if you insert at element 4, at index 4, it's going to move all of these elements over one position to the right. right? So it's going to move all the things in red over 1, right? And then we can insert our element into the freed up space, right? When you insert, right, you have to check, is there enough is there enough space in the is there enough capacity in the array to insert that extra element? If they're not, you have to make the array bigger. Right. You can insert at the end, so there is one function where you can use an invalid index, right? Insertion at the end of the list in many list implementations is legal, right? So to insert at the end, you pass in the size of the list, right? This list currently has 10 elements in it. So you can insert at index 10. 10's technically not valid, but for insertion it is, right? It's easy to implement. You just call add, right? Because add adds at the end of the list. So fortunately, it's just an if statement. Finally, there's removal. To remove the element at index 4, we're going to return the element that's sitting at index 4. To actually remove it, we're going to take the elements after index 4, so the ones in red, and we're going to just move them over 1 position to the left. Right, so we're going to shift everything 1 position to the left, and that overwrites the old element sitting at index 4. Right, and so to implement this thing, we need a way to shift a bunch of elements left or right. Right, and so we're going to look at a function that does that for us. Right, rather than writing a loop, there's a function that will actually move a chunk of memory for you. Right, and finally, am I using assert? Well, I'm going to use assert in the list. I don't remember if I use assert for the string or not. Hang on, let me just quickly check. I don't remember if that's how I handled the errors in the string implementation. Sorry, it's a bit of a long notebook. Do we assert anywhere? So it's going to be in the, not here. Do not alter, sorry, clear. Somewhere where I use an index, do we assert? Where's get? Get. We don't. Okay, so the notebooks is not using assert. The notebooks are actually checking the index and then returning null. Oops. So where's my lecture? There we go. All right, so to handle errors in the list implementation, I'm going to use the facility called assert. So you get assert by including assert.h. Assert's what's called a macro. It looks like a function, which is good enough for our purposes for now. A macro is actually not a function. It's a chunk of code that's been given a name. The preprocessor deals with the macros. The way you use assert is you write assert and then some condition inside around brackets. If the condition is true, nothing happens. If the condition is false, then the program stops running. So that's how I'm going to handle errors in the list. It's not the best way to do it, but that's how we do it for the list. Mostly so I can show you assert. You can turn off assertions via a compiler flag. So I don't know what the flag is for GCC. You'll have to look it up. You can turn them on when you're testing your code, and then you can turn them off when you're releasing your code, the final version of your code. By turning them off, you get rid of the condition checking here. Right? Basically, there's an if statement happening here. Right? You can get rid of those if statements at runtime by turning off assertions in the compiler. Okay, so let's look at our list implementation. So this is, we're going to look at a bunch of source code now. Okay, so step 1, we're going to make a header file. Right? So in our header file, right, the first thing we do is we write down our include guard. Right? Our type's going to be called list, right? Just all lowercase list. Right? The include guard names are typically written in all caps. You don't have to. You can put them in lowercase if you want. But most programmers write them in all caps. Right. We're going to need true and false, so I'm going to include standard bool here. All right, so here's our list. So there's the type def of our list. Right. So we have some struct called list. Right. For convenience, we're just going to call it list. Right. And so you use a type def to do that. Right. Now notice what's missing here. Right. There's a structure somewhere called list, but it's not in the header file, right? So if you look through this header file, you will find no definition of the structure list, right? So the definition of the structure is instead inside the source code file. So it's sitting over here, right? And so what this thing here is an example of is right there, right? So that thing there is called an opaque type in C. This is an incomplete type, right? We say that there's something called list, right? We're declaring a struct whose tag is called list, right? But the implementation's not here. So the type is incomplete, right? When you're making a data type, this is common to C, right? So it's common to see some type, in this case list, that's declared, but you don't know what the actual implementation is, right? So the user of the list type can't actually see what data members are making up the list, right? They don't have access to that, right? Unless they have access to the source code file itself, right? So the implementation details of the list type are hidden from the user, right? So that prevents whoever's using list from going into the list structure and accessing the array or the capacity or the size themselves, right? Because remember in C, there's no access modifiers, right? So anybody who knows what's inside of a list can just write something.capacity and fiddle with the capacity of the list, right? Or they can write something.size and change the size of the list, right? If you do that, that's probably going to screw up the rest of the list functions because now the list has a size that it doesn't know about, right? And so you can hide stuff, you can sort of hide stuff in a C program by using this technique, right? Provide them with a data type where they don't know what's actually in the data type, right? The way they use the data type is through the functions that are provided in the header file, right? So there's the extent of information hiding in C. It's not very, the extent is not very large, right? You don't have access modifiers or anything like that, right? There's no packages, there's no modules, there's nothing. Okay, so we're going to create a bunch of functions that basically return new lists. So these sort of look like Java constructors, right? So I have a list init empty. That's going to return a new empty list, right? It's going to return a pointer to a list, right? So the other thing that's common when you're using a data structure like list in C is instead of passing around or returning these things, right? So instead of actually passing around a struct, you pass around a pointer to a struct, right? There are good reasons for this. This string notebook tells you, actually lists the reasons for doing this, right? For now, just realize that everything in this header file is going to be either expecting, the functions will either expect pointers to lists, or they're going to be returning pointers to lists, right? So that returns a pointer to a new empty list, right? That returns a pointer to a list that's empty, but has that capacity, right? So you can add, so the user, if they want a very big list, they can call this function and pass in a large number for the capacity, right? List copy is basically a Java copy constructor. So it copies another list, creates a new list by copying the elements from another list. So here our other list is marked as const, right? And it's a const pointer in this case. So if you have a const pointer, what that means is that you cannot use the pointer to modify the underlying object. So what copy is trying to tell, what copy is basically advertising is you passed me a pointer to this list other, right? I'm not going to change the elements or the size or the capacity of the list other, right? That's what const is indicating here. Okay. So list size returns the size of the list, right? So you pass in a list. Again, it's const, so size is promising I'm not going to change the list that you pass in, right? And it returns the size of the list, right? Number of elements in the list. Get returns an element at that index in a list, right? Again, const, right? Because get should not change the list that it's accessing the element of. Set does change the element that it's accessing. So the list is not const, right? Set needs to modify the list t, or the list pointed at by t, so the parameter is not marked as const in this case, right? It changes the element at that index to that value. Right? Add adds to the end of the list, right? So that list is not const because we have to modify that list, and it adds that element. Insert inserts into the middle of a list somewhere. Remove removes an element from the list. List to string generates the string representation of a list. Again, you're going to see that that's a very long and convoluted function. And there's a second way that we're going to do it as well. Right? So there's two of these. Finally, if you go back to the here. So if you go back to the functions that create lists, right, they all tell you, right, this returns a list or returns a pointer to a list, right? So it's dynamically allocating memory for a list structure somewhere. At some point when you're done with the list, you have to free that memory. The problem here is that the caller has no idea what's inside of the list, right? So they don't really know if they have to free something inside the structure as well, right? You have to free the structure, but there might be something in the structure that you also have to free. There's no way for the user to know that because they don't know what's inside of a list. So you have to provide a function that also cleans up the contents of the list. So list free is the function that you call to return memory back, or that the user calls to return or to free the memory that's occupied by the list. All right, any questions so far? All right, on to the implementation. So it looks like we're going to need a lot of standard library header files, and we do. After you've included the standard library header file, so normally when you're writing your code, you don't know that you need all of these, right? As you're implementing the functions, you'll realize, oh, I need to include this header file, right? So you go back and include the header file, right? Don't forget to include your list.h header file, right? Now the very first thing inside of our header inside of our source code file is the actual implementation of the list struct itself, right? So what do you need to implement a list, right? So I need somewhere to put the elements, so I need an array. There's no generics in C, so here you have to decide on what's the element type, right? So for the time being, our list is only able to hold ints, right? If you want a list of something else, like a list of double, for the time being, you have to make a new data structure that corresponds to a list of double, right? If you want a list of car, you need to make a new data structure that corresponds to a list of car, right? There is no generic mechanism like there is in Java. We'll see how to work around that in a couple of lectures, right? For now, our lists are lists of int, right? I need an array, and it can't be a fixed size array, right? Because this thing has to change, it has to dynamically change its size. So I'm going to need a dynamically allocated array in this case. C arrays, they don't keep track of how big they are. So I need to keep track, or the implementer of the list type needs to keep track of how big is the array, right? What is the capacity of the underlying array, right? So we need to keep the capacity, right? And then finally, we need to know how many elements are in the list, right? And so that's the size of the list, right? The size is always less than or equal to the capacity. And so there's the structure that we're going to use to represent a list. The default capacity, that's just the starting capacity of a list if the caller doesn't specify otherwise. I've picked 4. That's probably too small, but whatever. You can put whatever number you want here. Right. We'll come back to add capacity in a moment. Right. Okay, so the first creation function creates and returns a pointer to an empty list. Right. Instead of duplicating a bunch of code, I'm going to call a different function. Right? So I'm going to call the list_init function, which initializes a list having a specified capacity. Right? So we're just going to pass in the default capacity and let the other function do all of the work. And there's the function that does all the work. Right? So to initialize a new list that's empty, right, and has that capacity, right, the very first thing you need to do is you need to allocate space for one of these things here, right? So I need to allocate memory for a list struct. Right? So, very first line of code, call malloc, right? Allocate memory that's big enough to hold one list struct. Right? So there's the list that I'm going to return. Right? Now that gives me one of these. Right? But it doesn't initialize that, or that. Right? I just get a block of memory that can hold a pointer, the size, and a size. Right? I now need to initialize these three values here. Right? So it's just like a Java constructor, right? Where you are now initializing the quote-unquote fields of your class. Right? Here I have to initialize the members of my struct. Right? If you wonder what new does in Java, new is basically doing the malloc. Right? So new in Java is allocating memory for the object. Right? It does some other stuff too. Right? But one of the primary purposes of new in Java is to allocate memory. Right? It's doing something akin to a malloc in C. Right? So there's my structure. I now fill in the members of the structure. Right? Step one, right? I need to allocate space for that array. Right? So I need to allocate that array. So again, there's going to be a second call to malloc. Right? So we call malloc. How big is the array? Well, it's that big. Right? Remember that malloc expects the size in terms of multiples of char. Right? So my array is an array of int. So it's that many ints, and I need to multiply that by how big an int is on this computer. Right? So you multiply the capacity by the size of int. Right? If you just write capacity, you've got an array of char, or an array that can hold that many chars. Right? I need an array that can hold that many ints. Right? So I have to multiply by size of int. Right? Now remember, malloc can return null if it fails. So I'm going to check, are either of the two pointers null? You really should check T first, and then you should check array test ARR here. I got lazy and did it here, but you really should check here and here. Right? If it fails to allocate either the structure or the array of the structure, it returns null to indicate to the caller that it could not allocate a list. Right? So there's an example of indicating error, right, by returning null. Right? C has no built-in exception mechanism, right? And so there's no way to throw an exception in C. Instead, error conditions in C are often communicated by the return value, right? So here we're saying that if the return value is null, something's gone wrong in the we were unable to allocate this this list. Okay, if malloc succeeds, right, I can store a pointer to that array in the structure itself. Right? So now in T, right, we can set the member ARR. Right? That's just equal to the chunk of memory that we just allocated. Right? I can now set the capacity. Right? And then I can set the size to 0. Right? I don't know if I fixed this on OnQ or not. There was a missing return statement at one point in time. Right? So this thing now returns a pointer to the allocated structure back here. Right? And you've now got an empty list that you can now use. All right. Any questions there? Okay. So make a list by copying another list. Right? So it's going to be similar to this function here. Right? So this function here makes a list having that capacity. Right? If I want to copy another list, then I need to make a list having the same capacity or larger as the other list. Right? So I could call list init, but instead I'm going to rewrite this all over again. Right? Step 1, allocate memory for the structure itself. Right? So allocate enough memory to hold one list structure. Right? Step 2, allocate memory for the array inside the structure. Right? So how big does that array need to be? It needs to be at least as big as the other list's capacity. Right? So we're going to allocate an array of int whose capacity is the same capacity as the other list. Right? Now that I've got an array big enough to hold the elements, I would like to copy the elements from that list into the, from that list's array into this list's array. And so the function we're going to use here is memcopy. Right? So memcopy copies a block of memory. So memcopy is defined in standard lib. So if you go here to headers and into standard lib. Well, wait. It's either standard lib or string. Hang on just a second here. It's one of the two. It's string. I don't know why they put it in string. Scroll down. Somewhere at the bottom of this, here it is. The character array manipulation. So we want memcopy. Okay, so memcopy, that's the one that we're looking at here. Memcopy copies an amount of memory equal to count. Right? Now remember in C, count is always, the amount of memory is always a multiple of car, right, of the size of car. So that thing there is the multiple of a size of car, right? It's not necessarily the count, right? So be very careful with that, right? It copies that much memory from this array into that array, right? So destination, that's the destination array. Source, SRC, that's the source array. Count, that's the number of bytes, right? Number of characters that are going to be copied. Oh, there are some restrictions here. So I have to make this a little smaller. Okay, so when you're using memcopy, right? If you're copying from the same array into the same array, you have to be careful that the objects do not, you have to be careful that the parts of the array you are copying do not overlap, right? So you are allowed to copy from one array into the same array, but if the parts of the array that you're copying from and into overlap, memcopy is not guaranteed to work properly. There's a different function that you have to use if the memory is overlapping, right? And so when we start to shift elements from one place to another in the same array, you're going to see a different function, right? The other function can handle the overlapping memory, right? Memcopy can't do it. Here we're copying from one list into another list, so we don't care, right? We don't have to worry about that. So here we're going to copy from the other array, right, into our newly allocated array, that much memory, right? So how much memory are we going to copy? Well, we're going to copy all of the elements of the other array, so that's other.size, or other arrow size, right? And then don't forget to multiply by the size of the element type, right? Because this is the number of characters or number of bytes that are being copied, right? So copy that much memory from here into here. Right? Now we can set the capacity of our new list to be equal to the capacity of the other list, and we can set the size of our new list to be equal to the size of our other list, and then return t. Right? Okay, one last function, and then we'll call it quits for today. Right? To get the size of a list, it's very easy. Right? Our structure has a field has a member called size, so we just return t arrow size in this case. Right? Again, the list that's passed in is const, right? It's const because we're not going to change the size of t, or we're not going to modify either the array, the capacity, or the size of t. Right? All right, so we'll finish up the implementation of list in the next lecture. Don't forget you have a quiz tomorrow, right, in class. Hello.